Analyze the graph of the function r of x equals x squared over x squared minus x minus 2. So I'll go through each one of these parts. This is sort of a long process, so bear with me. First, we want to factor the numerator and denominator. So we have r of x. The numerator is already in factored form, but the denominator can be factored into x and x, 2 and 1, the minus on the 2 and the plus on the 1. This is helpful in finding the domain. So this is going to help us find out that the value of 2 and the value of negative 1 need to be excluded from the domain because they're going to cause a 0 in the denominator, and division by 0 is undefined. So our domain is x such that x is not 2 and x is not negative 1. Then we want to write our function in lowest terms, and since there are no common factors between the numerator and denominator, this function already is in lowest terms. Then we want to find any x-intercepts of the graph, x and y-intercepts. So let's find the y-intercept first. It's a little bit easier. So to find a y-intercept, you're going to let x be equal to 0. So we have r of 0 is 0 squared over 0 minus 2, 0 plus 1. And this ends up being 0 over negative 2 times 1, which is 0 over negative 2, and that's 0. So we have a y-intercept of 0, 0. So then we'll find the x-intercepts and also the behavior at those x-intercepts. So our function r of x equals x squared over x minus 2 times x plus 1. To find the x-intercept, we're going to let y equal 0. That's setting r of x equals 0. That's 0 equals x squared over x minus 2, x plus 1. We can solve this by multiplying both sides by x minus 2 times x plus 1. On the left, 0 times anything is 0. On the right, x minus 2 cancels, x plus 1 cancels, and I get x squared equals 0. And that gives me x equals 0. Now the behavior around that x-intercept we get from this multiplicity right here. So we have an x-intercept of 0 with multiplicity that is even. And so that means that at that x-intercept, the graph is going to touch the axis rather than cross the axis. So for that x-intercept, you would touch the axis. Then we want to find the vertical asymptote if one exists. And this is where it comes into play what we did earlier about writing the function in lowest terms. You want to make sure that you've canceled out any common factors before you try to determine the vertical asymptotes. We said that this function already was in lowest terms, so to find the vertical asymptotes, we would set those denominators equal to 0 and solve. And we have two vertical asymptotes for this function, a vertical asymptote at x equals 2 and a vertical asymptote at x equals negative 1. Now we want to determine the behavior of the graph on either side of the vertical asymptotes. Now what we mean by that is we want to know if the y value is approaching infinity or negative infinity on either side of that vertical asymptote. Because the definition of a vertical asymptote says that x is going to approach that number, and either the y will approach infinity or negative infinity. And we need to know what's happening. So I'm going to make a chart using my vertical asymptotes to help me decide what to do here. So I'm putting on my number line a -1, that's the location of one vertical asymptote, and a 2. I'm going to go ahead and put open circles on those values because I know that those are not included in the domain. So what I want to do is choose test points around that vertical asymptote and the other vertical asymptote and determining what's happening to the y value, and that's going to help me know whether it's going to negative infinity or positive infinity. So for my test point here, I'll choose -1.5. I'm trying to choose something that is close to -1, and on the other side I'll choose -0.5. For the other vertical asymptote, I'll choose 2.5 and 1.5. And we're going to substitute those into our rational function, and we're looking for whether the y value comes out positive or negative. If it comes out positive, it's going to positive infinity. If it comes out negative, it's going to negative infinity. So my test points are -1.5, -0.5, 1.5, and 2.5. It might be helpful to do this with the calculator, but we're going to substitute into x squared over x minus 2 times x plus 1. You can certainly do this by hand, but I'll show you some features in the calculator that are helpful. So in my y equals menu, let me adjust this a little bit so you can see the whole thing. In my y equals menu, I will type my function. Let me do that in y1. X squared over, I'm going to put double parentheses, x minus 2 and x plus 1. And close that double parenthesis. Now then I'm going to go to the table. Now let's actually go to table set. So I hit second and window, which is table set. And what I want to do is I want my independent variable to be in ask mode. In ask mode, I'm going to be able to type which x values I want to plug in. So now I'll go to the table and type in the y values that I want. -1.5, -0.5, 1.5, and 2.5. So remember, all I care about is the sign here, positive or negative. So for the first one, we got positive. The next one, we got negative. And then another negative and a positive. Okay, now let's go back to my chart. Now using the chart, what we found is that on this side it was positive, on this side it was negative. And then we have negative here and positive here. So what that tells me is that when I have my vertical asymptote, because it's positive on the left, the graph will be approaching infinity on the left. And because it's negative on the right of that asymptote at -1, my graph will be approaching negative infinity on that side. Same thing for the other vertical asymptote at 2. We got negative on the left and positive on the right. In the next part, we're going to try to determine the horizontal or oblique asymptote of our function. So to find the horizontal or oblique asymptotes, we need to follow this set of rules that have been summarized for us using calculus. So the rules use the degree of the numerator and the degree of the denominator, and it compares the degree of the numerator with the degree of denominator in these different cases. So for our example, our degree of the numerator, which I'll call n, is 2. And if we remember, this original expression had an x squared in it as well if we multiplied that out. So the degree of the denominator is 2 as well. So if we look at our cases, we have a case here where the degree of the numerator is equal to the degree of the denominator. So in that case, we're going to have a horizontal asymptote, and it's going to be the line y equals a sub n over b sub m. Now what that is the leading coefficient. And the leading coefficient are these coefficients that are attached to the highest degree term. So for our example, the highest degree term is this x squared, and we're going to have a coefficient of 1 here. And both of these have a coefficient of 1, and 1 times 1 is 1. So we have a leading coefficient, or our a sub n, for the numerator will be 1, and our b sub m, our leading coefficient for the denominator, will be 1 as well. So our horizontal asymptote is the line y equals 1. We just determined that we have a horizontal asymptote at y equals 0. And the next part we want to focus on is if the graph intersects that rational function. So we want to take a look and see if our graph will intersect that rational function. So the way we do that is we set the rational function x squared over x minus 2 times x plus 1 equal to our horizontal asymptote. This is going to tell us when they're equal to each other, when they overlap, when they intersect. So to solve this, I would multiply both sides by x minus 2 times x plus 1. This is going to allow me to clear the fractions. That cancels out these fractions from the left. And on the right, I'll multiply that out to get x squared plus x minus 2x minus 2. That's x squared equals x squared minus x minus 2. I can solve this equation by subtracting x squared on both sides. That gives me 0 equals negative x minus 2, and I can add x on both sides, and that gives me x equals negative 2. So for this example, the graph will intersect the horizontal asymptote at the value of x equals negative 2. That y value will be 1 for the horizontal asymptote. So the point where the graph crosses the horizontal asymptote will be the point negative 2, 1. So up to this point, we've gathered a lot of information that will be helpful for us to graph our rational function. We found that we have an x-intercept at 0, which is going to touch the axis instead of crossing it. We have a y-intercept at 0. We've got two vertical asymptotes at negative 1 and 2. We found a horizontal asymptote at y equals 1. We found that the graph will cross the horizontal asymptote at negative 2, 1. And we also have worked out what the end behavior will be around those vertical asymptotes. So that's very helpful. So let's see if we can come up with a sketch of the graph. So we have our x-intercept and y-intercept at 0, 0. We have a vertical asymptote at -1. So I'm going to draw, let's use a different color. I'm going to use red. I'm going to draw a vertical asymptote at x equals -1. And another vertical asymptote at x equals 2. Sketching these lines out help you. It guides you how to draw the graph. We also have a horizontal asymptote at y equals 1. Let me bring that ruler back. Y equals 1, we have a horizontal asymptote. I'll draw a dashed horizontal line at y equals 1. And we have the point -2, 1. The point -2, 1 right here is where the graph crosses that horizontal asymptote. And then using my end behavior, I'll start at that point -2, 1, and I know I should be approaching the vertical asymptote going towards infinity on the left of -1, that vertical asymptote. On the other side, it'll come cross that asymptote and then start approaching the horizontal asymptote. Then on the other side with 0, 0, I'm going to be approaching -infinity on the right side of that asymptote and -infinity on the left side of the other asymptote. And then I don't have any points in this final section on the right, so I'd feel a little bit more comfortable if I picked one value, let's say an x of 3. So if I take an x value of 3 and substitute it into my function, r of 3 would be 3 squared over 3 minus 2 times 3 plus 1. It's 9 over 1 times 4. That's 9/4, which is about 2 point something, just a little bit more than 2. So at 3 and 2 point something, that would be about right here, I'm going to approach the vertical asymptote going to positive infinity and then approach the horizontal asymptote this way. Thank you for checking out my videos. Have a great day.